Good morning, everyone. Welcome back to our course, Network Analysis and Transmission Lines. Today, we are going to discuss about the transient analysis of RL circuits having DC excitation. So that means here, we are going to find the response, transient response of a RL circuit with the DC source, right? So these are the outcomes of our presentation. So one is we are going to, the final aim of this presentation is to obtain the transient response of RL series circuit. In that, we are going to have the current expression, transient current expression of a RL series circuit. Along with that, we are going to find the voltage across the resistor and also the voltage across the inductor. And we are going to look into the value of the time constant, and also we are going to calculate the power across the resistor and the inductor. So coming to this, so let us consider a series RL circuit as shown in this figure. So where you can see here a series RL circuit, so that means where a resistor R is in series with inductor L. Inductor L. Right. So let us consider the current in this loop is I. As mentioned here, the current in this loop is I. So as we said, we are going to find the response of the transient response of the series RL circuit. That's why we have connected a resistor and the inductor in series, having DC excitation. So we have considered a DC source over here. We have considered a DC source, right? So now, so in the initial conditions, that means at t is equal to 0. At t is equal to 0 or t is equal to 0 minus. Let us consider t at t is equal to 0 minus. The switch is open. Right? Now at t is equal to 0, the switch is closed. The switch is closed here. The switch is closed. So here it is a series RL circuit, not the RC. So please make a correction over here. Sorry for this. And here it is a inductor. Here it is a inductor. So now applying KVL to the circuit at t is equal to 0 when the switch is closed, we can have the V is equal to, what is KVL states? The EMF acting across the loop is equal to the sum of the potential differences across different elements in the loop. So what is the EMF? V is nothing but your EMF. V is nothing but your EMF, which is equal to the sum of the potential differences across different elements. What are the different elements in this loop? One is the resistor and the other one is the inductor. So what is the potential difference across the resistance? The current into the value of the resistance. So here we have considered the resistance as R. So what is the current? I. So I into R plus L di by dt. L di by dt is your voltage across the inductor. So this expression we got, I think we have already derived this expression when we are discussing the self-inductance concepts in the module 1 or unit 1, right? So now, as we discussed in the previous lecture, we are going to solve this, or we are going to obtain the response of this RL or RLC circuits using the differential equation approach. So now we are converting into the general form of the differential equation. So to convert into that, so here in this expression, I am taking L as common in this. So in this equation number 1, which we obtained by obtaining the KVL, so in this expression, I am taking the L as common. So if we take L as common in this, we are going to have di by dt plus R by L into I plus R by L into I, which is equal to, if you take L as common, this L if we send this side, we are going to have V by L. So we are going to have the final expression as di by dt plus R by L into I is equal to V by L. Now if we closely observe this equation number 2, let us say this is the equation number 2. Now if you closely observe this equation number 2, you can see this, it is in the form of the linear differential equation. Which type of linear differential equation? It is in the form of the non-homogeneous differential equation. Why it is non-homogeneous? Because it is in the form of dx by dt plus px is equal to k. If it is 0, you can say it is a homogeneous differential equation. But here we are having a constant k. So that means here this is in the form of the first order non-homogeneous linear differential equation. If you compare this with the general equation which you have studied in the mathematics, that is, which is nothing but dx by dt plus px is equal to k. So this equation can be of different forms with respect to different textbooks or materials. If you look into the mathematics by I think Ashant publishers, if you look Iyengar's textbook, it will be there like dy by dx plus py is equal to q. Whereas in the different textbooks, it will be in the form of dx by dt plus px is equal to k. So different forms you can see. So don't confuse within that. So the form is same. So now if we compare this equation which we obtained from the series RL circuit, that is nothing but di by dt plus r by L into I is equal to V by L. You can see here. So the same form where dx by dt is nothing but the di by dt and px is nothing but where this x is nothing but here I and this p is nothing but, what is this p? P is nothing but r by L. P is nothing but r by L here. P is nothing but R by L. So, and what is K here? K is nothing but V by L. K is nothing but V by L. So, this is the value of K. So, now for this form where dx by dt plus px is equal to K, you have already solved the solution for the first order non-homogeneous linear differential equation. What is the solution? The solution is going to have two parts, that is nothing but two responses. One is nothing but the complementary function and the other one is nothing but the particular integral, right? So what is that? The x is equal to e power minus pt integral of k into e power pt dt plus c into e power minus pt. So in this c into e power minus pt is nothing but your complementary function. So this is nothing but your complementary function. So what is this? So this c into e power minus pt is nothing but your complementary function, whereas you can see this e power minus pt into integral of k into e power plus pt is nothing but your particular integral. This portion is nothing but your particular integral. So that means we can write this as x is equal to, where is this x is equal to, what is this? The particular integral, that is nothing but xp plus xc. xc is nothing but your complementary function and xp is nothing but your particular function or particular integral. So this is what the format with respect to the first order, the solution for the general form of the first order non-homogeneous linear differential equation. So now writing the same solution, the solution for this equation, that is nothing but the equation number 2 in terms of I, the solution for I, we need to obtain the solution for I by comparing with the general form of your first order non-homogeneous linear differential equation. So how to obtain this? Now what we can see, just replace this, the same expression where p is nothing but x is equal to I, and P is nothing but what is P? P is equal to R by L, and K is nothing but V by L. K is nothing but V by L. Same. Whereas here, this C, this particular C is nothing but your arbitrary constant. This particular C is nothing but your arbitrary constant. So let us look into this. So where C is the arbitrary constant, so in a similar way, we can write the current expression as where P is nothing but the R by L, and we can write, and K is nothing but the V by L here. So we can write I is equal to, what is I? I is equal to C into, where this C is nothing but the arbitrary constant here, C into e power minus PT. P is nothing but R by L, right? So this part is nothing but your complementary function. This part is nothing but your complementary function. This is nothing but your IC. We can write it as complementary function IC. So whereas this portion is nothing but your particular integral. So in terms of I, we can write it as particular integral as IP. This is nothing but IP, right? So now, using the initial conditions, by solving this equation, we can come across, this is the final expression, that is nothing but I is equal to C into e power minus R by L into T plus V by R. How we came across this equation is the question here. So if you well good enough in the mathematics, you can easily get it this one, but let me explain this again. So now, so when the switch is closed at T is equal to 0, so at T is equal to 0 minus, that is just before closing the switch S in the circuit, which we have shown in the previous slide, right? The current in the inductor is going to be 0. Why the current in the inductor is going to be 0? Right? So that means here, the current through the inductor just before the switching is same as the just after the switching. The moment before the switching is going to be same as the moment after the switching. So what is the current before switching? If we estimate the initial conditions, before switching is T is equal to 0 minus is, the current is 0 because the switch is open. So immediately just after the switch is closed also, the current through the inductor we can observe it as 0. Why? Because due to the electrical inertia, we can say due to its electrical inertia of the inductor, which is the basic property of the inductor, following the rules of your Faraday's electromagnetic induction, Faraday's law of electromagnetic induction, we can say the inductor doesn't going to allow the sudden change in the current. So that is the reason why the current through the inductor just before the switching is going to be same as the just after the switching. So that is the reason if we estimate the initial conditions at T is equal to 0, the switch is closed and the current remains 0. So just substitute these initial conditions over here. That means T is equal to 0 if we can write. So what we can have here is, so writing this e power minus R by L into T is equal to 0 means, so this whole portion is going to be 0. So e power 0 is going to become 1. So 1 into, so we are having this V by L as it is, so which is equal to V by L as it is. We are having this V by L as it is, and now you can see V by L into constant here. So integral of e power R by L into T. What is this integral of e power R by L into T? Integral of e power R by L into T means integral of e power x. E power x is nothing but e power x into, what is e power x? E power again R by L into T. Again e power R by L into T. Right? again r by L into T into what is the constant? R by L. So this is going to become L by R, 1 by x, right? 1 by x into e power x. The integral of e power x is nothing but 1 by x into e power x. So this is going to be our equation. So now again, if you substitute the t is equal to at t is equal to 0, so this is going to be equal to 1. E power 0 is going to be equal to 1. So now, and here this L and this L, denominator L and the numerator L is going to get cancel over here, and we are going to have 1 into V into 1 into 1 by R. So which is nothing but V by R, which is nothing but V by R here, which is nothing but V by R. Is it clear? So now, using the same initial conditions in this complementary function also, to determine the value of C here, what we can write it is, so what we can write here? What we can write? So here we can write, so at t is equal to 0, so if we obtain the value of C here, to obtain the value of C, again substituting the initial conditions, at C is equal to, so what is the value of C? At t is equal to 0, so this e power minus r by L into t is going to become 1 here. So if this is become 1, C into 1 is plus V by R is equal to I. That means at t is equal to 0, this I also going to become equal to 0. So this is going to be, this I is going to be 0 at t is equal to 0. Right? Because the current through the inductor at t is equal to 0 minus is going to be same as the t is equal to 0 plus. Instantly, the current just before switching is going to be same as the just after switching. So this is what the little confusion going to be there here, but you have to understand this. So because the same initial conditions we are going to apply for all kinds of RL circuits, RC circuits and RLC circuits, everything. So now, estimating the initial conditions at this, at I is equal to 0, we are going to find the value of this arbitrary constant C. So what could be the value of the arbitrary constant C here? C is equal to C into 1 plus V by R is equal to 0. Then what is the value of C? C is equal to minus V by R, minus V by R. So if we, instead of substituting the initial conditions in the particular integral, we can also integrate directly. Even that also we can have the equation V by R here. Because here we are having the minus R by L into T, and here we are having the plus R by L into T. So minus plus is going to get cancelled over here, and there also you are going to have e power 0, and finally you are going to get e power 0 into V by L into L by R. So L and L is going to get cancelled there also, and we are going to have V by R here, right? So we are going to have the value of C as minus V by R, minus V by R, right? So now substituting the above conditions, we can have the C is equal to minus V by R. So now substituting the C is equal to V by R in the previous equation, that is, we can have C is equal to minus V by R. So that is I is equal to, so here that means here I am substituting in this equation. C is equal to V by R minus V by R. I am substituting in this equation and obtaining the final transient current expression. So I is equal to minus V by R into e power minus R by L into T plus V by R. Now taking common as V by R in this equation, we can have V by R if we take common. So in this we are going to have 1, as here is minus 1 minus e power minus R by L into T. Minus R by L into T. So if we obtain the response graphical response of this equation, the current I, we can have the same equation, that is nothing but V by R into 1 minus e power minus R by L into T. We can see it is nothing but exponential increase over here, because it is 1 minus e power minus R by L into T, right? So that is nothing but, so in this equation, so the first term is going to be our transient response. The first term is going to be transient response. Why? Because it is transient response in that sense. So this is the function of the t. So that is the reason why it is nothing but your transient response. Whereas the second term is now nothing but your the steady state part, the steady state response. This is going to be our steady state response, and this is going to be our transient response. So that means, so this is the steady state value, that is nothing but V by R here. So that means when the response is transiting from 0 to V by R, the short spell of time here, this spell of time is nothing but your transient response. So this is nothing but your transient response. This is nothing but your transient time. We can say with respect to the x-axis, this is nothing but your transient time. Where the steady state means, so this is going to settle at some value. That value is nothing but V by R. That value is nothing but V by R. So this is going to be the final expression for your the current expression of the transient current expression of a series RL circuit with DC excitation. This is going to be our final expression. That is nothing but I is equal to V by R into 1 minus e power minus R by L into T. So this equation we should remember clearly for the quicker solution, to obtain the quick solution when you are solving the some numericals, right? So you can solve directly also as per the problem, but it may take some more amount of time. Again, if you write the differential equation, obtaining the solution of the differential equation, everything is going to take much more time. So to avoid those kind of things, you have to remember, it's better to remember this equation. That is nothing but I is equal to V by R into 1 minus e power minus R by L into T. So this is going to be our transient current expression for a series RL circuit with DC excitation, right? So now if we observe one more analysis from this, so that is nothing but, so in the previous expression, if you see the previous expression over here, which is nothing but V by R into 1 minus e power minus R by L into T, we can have this the constant. We can, as R and L are the constant values of a, because these are the values of the resistance and the inductor. So this is going to be nothing but, so we can write the same expression as e power minus t by tau. So this expression here, we can write it as a e power minus t by tau. So where tau is going to become equal to the, tau is going to be equal to the, what is the tau? Tau is going to be equal to the L by R, which is nothing but the time constant of a, LR circuit, series LR circuit or RL circuit. So now for better analysis with respect to the time constant tau, so let us take the transient part of the solution, that is nothing but V by R into minus V by R into e power minus t by tau. T by tau means t into R by L. As tau is equal to L by R, we can write it as t by tau. Is it clear? So now with respect to the time constant, let us say the tau is equal to, at t is equal to tau. That means at t is equal to tau, because this is nothing but I of tau. At t is equal to tau, if you consider the time constant is 1, so it is going to be equal to minus V by R into e power minus t by tau, which is equal to, so this is going to be minus V by R into the t and tau. If we consider it as an equal here at the first instance, that is at the t is equal to 1, the first instance, we're going to have e power minus 1, which is going to be equal to minus 0.368. 0.368. So now if you convert this into the percentage, it is going to be equal to the 36.8%. So that means the transient response at first instance, it is going to reach it 36.8, only 36.8% of its initial value. Only 36.8% of its initial value at t is equal to tau is equal to 1. Right? At the first instance. Similarly, if you go for the second instance, that is at 2 tau. So that means at 2 tau, if you consider, so e power minus 2, e power minus 2, so we are going to have 0.135 V by R. Right? So it is going to be vary accordingly. So it is going to reduce. But if we take with respect to the complete value, which includes the steady state and the transient value, that is nothing but V by R into 1 minus, that is the previous expression which we are having. So that is, so this one, I is equal to V by R into 1 minus e power minus R by L into T. So now if we analyze with respect to the time constant, the same expression, we can have the different values. If you want, you can check it out. Because here we are going to have 1 minus. So that means as shown in the next figure, so 1 minus e power minus t by tau means you are going to have 1 minus 0.368. So 1 minus 0.368 is going to become around 73 or 74%. So this is what the difference you have to observe with respect to the time constant analysis of a series RL circuit. Right? So if you include the steady state portion of the steady state current also, the response is going to be have a wide change in the response if we calculate the individually with respect to the transient part. The transient part is going to reach almost 99% only after the 5 TC or the 5 tau. At 5 tau only we are going to have the large value here. Is it clear? So that is what the case with respect to the time constant here. Now our next task is to calculate the voltage across the inductor and also the voltage across the resistor. Voltage across the inductor and the voltage across the resistor. So if we calculate the voltage across the resistor, we can have here voltage across the resistor. You can see, so that is nothing but the voltage across the resistor. What is the voltage across the resistor? Simply follow the Ohm's law. According to the Ohm's law, what is the voltage across the resistor? VR is going to be equal to R into I. R into I. So what is R? As it is R into I is nothing but what is the I? We have obtained it. The transient current expression for the RL circuit we have obtained. That is nothing but I is equal to V by R into 1 minus e power minus R by L into T. Just substituting the same value over here and we are going to have the value, the final value, that is nothing but VR is equal to V into 1 minus e power minus R by L into T. So here you can see, so this is the R and here also in the denominator we are having R and this R is going to get cancelled. So we are going to have V into 1 minus e power minus R by L into T. So this is the expression for the voltage across the resistor. And similarly, if you want to obtain the voltage across the inductor, that is nothing but VL is equal to L dI by dt. L dI by dt. So here we are having a one more step extra because we are having a derivative. So L into what is the derivative here? So the derivative of the I, the derivative of V by R into 1 minus e power minus R by L into T. So the derivative of this is, if you find the derivative, you can have the expression that is nothing but V by R into e power minus R by L into T into R by L. So again same Amma. Again same. You can apply the integral, so derivative of e power x and you can get the value here. As V by R is the constant, taking the removing the constant out, we can have this value. So in this also, if you observe closely, this is the R in the denominator and this is the R in the numerator. So this both is going to get cancelled over here. So we are going to have the final expression that is nothing but, so VL is equal to V into e power minus R by L into T. So this is the expression for voltage across the inductor. This is the expression for voltage across the inductor. Right. So now simply calculating the power in the resistor and the power in the inductor. So this is the power in the inductor. So power in the inductor L. So this is the PL here. So PL. So power in the resistor is nothing but the voltage into the current, transient current into the voltage drop. So VR into I, which is nothing but equal to VR into, so that means V into VR is nothing but, so what is obtained here? What is the value we have obtained here? VR is nothing but V into 1 minus e power minus R by L into T, right? Into what is I? What is I? I is nothing but V by R into 1 minus e power minus R by L into T. So multiplying this, V into V by R, we are going to have V square by R. V into V by R is nothing but V square by R into, so 1 into 1 is going to become 1, and 1 into e power minus R by L into T, and e power minus R by L into T into 1. So we are going to have 2 minus 2 into e power minus R by L into T plus e power. So multiplying these two, we are going to have minus into minus is going to become plus, minus e power. So if you multiply this, minus into minus is going to become plus here. So plus e power minus R by L into e power minus R by L into T. So it is going to become minus 2R by L into T. Minus 2R by L into T. So this is going to be a final expression for the power in the resistor. Power in the resistor, which is nothing but V square by R into 1 minus 2 into e power minus R by L into T plus e power minus 2R by L into T. So next, coming to the power in the inductor. So power in the inductor. So which is nothing but PL. So PL is nothing but again VL into I. So VL into I. So what is VL into I? So what is VL? So we are having VL already here. So this is nothing but VL. Now substituting the same expression over here, VL is nothing but same expression I am substituting here, which is nothing but V into e power minus R by L into T into I. So I we already obtained, that is nothing but the transient current expression, that is V by R into 1 minus e power minus R by L into T. So by multiplying these two again, so what we are going to have, V into V by R, V into V by R here. So V square by R. So V into V by R is going to become V square by R, and into 1 into e power minus R by L into T, e power minus R by L into T, minus e power minus R by L into T into e power minus R by L into T is going to become e power minus 2R by L into T. So this is going to be our final expression for the power in the resistor. So now, so this is what the different values which, as we discussed in the outcomes, we have obtained the transient current expression for a series RL circuit, and also we have obtained the voltage across the resistor of a series RL circuit, and also we have obtained the voltage across the inductor of a series RL circuit, and also we have obtained the power through the resistor and the inductor in the series RL circuit. So using these values, using these formulas, we can solve many numericals. So the numericals that we are going to solve later. So this is what the derivation part with respect to the series RL circuit, the transient response of a series RL circuit having DC excitation. Remember, having DC excitation. So if we include the sinusoidal excitation, it's going to be much more complex equations where we are going to involve the second order linear differential equations also in the upcoming lectures. So be thorough with the first order linear differential equations, the concept of the linear differential equations. So this is what with respect to the transient response of series RL circuit. So if we plot the graphs for this VR, VL and PR and PL, you can see the voltage and with respect to the time constant if we plot. So we can see what is the expression for VR. VR is nothing but V into 1 minus e power, right? So V into 1 minus e power means it is exponentially increase is going to be there. VR is going to be exponential increase because it is 1 minus V into 1 minus. So V is nothing but represents the steady state part. So V into 1 minus e power. So 1 minus means it is the increasing. It is a positive. So whereas coming to the VL, if we observe the VL, so VL is nothing but V into e power minus L. That is, it's a negative. So that is the reason why it is going to be V into, from the steady state V value, it is going to decay, exponential decay. V into e power minus R by L into T. With respect to the time constant, it is going to decay. Similarly, with respect to the power, PR and the PL values also. This is what the responses for the graphical responses for the voltage across the inductor and the resistor and the power through the resistor and the inductor. Thank you very much.